This is a perfect example of how first impressions aren't always right. When I first saw the image this Amstrad CPC was outputting, I was convinced it was due to a faulty CRT controller. So much so that I named this episode CRTC Repair. But once I started digging, things kept pointing in a different direction, until at the very end, I tracked it down to a very different chip.
Hello and welcome back to Noel's RetroLab. The case of this particular Amstrad was pretty interesting to me because it wasn't just the generic black screen or the famous gray rectangle in the middle that usually indicates bad RAM. Here we clearly have some video signal, but it's completely wild and incorrect. So I thought this would make for a good deep dive into the video signal generation of the Amstrad CPC. Oh yeah, and we can fix it too.
One of my Patreon supporters, Marcos, found this Amstrad CPC 464 in a closet. Apparently used to belong to his uncle, and when he turned it on, he got that Garbled video that we saw earlier. As luck would have it, Marcos lives just a few kilometers from me, so he brought it in person for me to fix and make a video out of the process.
Okay, so we get the exact same problem that he described and that we saw in that video. So the first thing to do is to figure out, is the problem coming from here or from here? Actually, one thing we can do right away is turn up the volume and listen. Okay, if the computer was working fine and it was just the monitor, we would be hearing a beep, beep, beep sound, and there's nothing like that. I'm gonna guess it's coming from here. To find out for sure, I'm just going to connect this to our external TV and see what happens. And nothing happens. I don't even get a light in here. Let's see what we find inside. And so why would we not have power? The DC jack definitely moves a little bit. So it could be the typical dry joint. So let's unscrew the board, look at the other side, and see what's up with the power jack. Oh, wow. Yeah, say somebody's been there. I think I'm just going to remove that and make sure they're connected correctly. Okay, so yeah, we can start seeing things a little bit better. You can see how that track, and that's the 5 volts coming from the power supply, is broken there. Oh, I see. The pads were broken. Even this one. Yeah, this pad is lifted. Look at that. So that's why they had to do this botch job in there. So somebody probably replaced this because there was probably some dry solder joint. I'm still wondering why it didn't work the second time we tried it. All right, that's still not super pretty because we're missing the pads, so really those blobs of solder are almost there more for a mechanical reason than for an electrical reason. It actually doesn't move anymore. Okay, so first I just want to see if it draws any current. Still doesn't draw any current. So even though the switch is not on, we should be able to see 5 volts difference between this and this. And we're getting 0. Yeah, this DC jack, I didn't want to take it out because there was like the remnants of one little pad, but I think it's just not working right. Oh, so I think I see the problem. This is the old DC jack, and the barrel would make ground contact in the plate at the bottom, and that looks to be a little rusted. This one is nice and shiny, so this should be fine. Connected with a new jack. Okay. We get some current draw. That's good. Now we can see what kind of image we get. And we get absolutely nothing. Interesting. I suppose the signal could be so bad that this particular TV doesn't even interpret it as a signal like the monitor did. So it's telling us no signal. So just to be sure, let's connect it to the CRT TV. And oh yeah, there we go. It's all garbled video. There's clearly something, but the TV can't sync to it.
The video signal is generated by the gate array from the contents of the screen area of the RAM. It has pins that output R, G, B, and a sync signal. RGB are already analog signals, and each color can have 3 different states. And how exactly does the gate array know the data to generate that signal? It must read from the screen area of the RAM with the right timings and output those signals. That makes sense, except that the gate array doesn't have access to the address bus. And no access to the address bus means the gate array can't ask to read data from a particular address. Instead, it needs to have a read to it. And that's where the CRT controller kicks in. The CRT controller is clocked from the gate array, and one of its jobs is to generate the addresses to generate the video signal. Not to generate the video signal, just the addresses. So it goes something like this. The gate array tells the CRT controller, "Hey, give me another byte." The CRT controller hears that and puts the correct address in the address bus. The gate array then sets some control signals to trigger a read from that address and reads it from the data bus. Right after that, it quickly generates the signals from that pixel and outputs them in the right pins. Additionally, the CRT controller also generates the horizontal and vertical sync signals, which are sent to the gate array directly. The gate array then uses those to know when to generate the sync signal. And to make things a little bit trickier, all of this is done while the CPU isn't looking. The designers used some clever tricks and timed memory access perfectly while the CPU isn't using it. So the CPU can run at full speed and all memory can be accessed equally quickly, and the gate array coordinates things and decides when the RAM is getting addresses from the CRT controller and when it's getting them from the Z80. Actually, that's a bit of an oversimplification. The gate array does stop the Z80 potentially once every 4 microseconds. Sometimes it won't slow things down at all, sometimes it will a little bit, depending on what the Z80 is doing at the moment. And actually, things are still more complex than that, because the address bus is 16 bits, but the RAM needs to have the address fed in 2 parts, row addresses and column addresses. And that applies to both addresses coming from the Z80 and the CRT controller. So the gate array is really juggling access to the address bus like crazy to get everything running smoothly.
In order to do any measurements on the gate array, we need to remove the heatsink. And it doesn't matter if we run it for a while without it. I mean, it gets a little hot, but it can run without this for probably hours. So that should not be an issue. So we'll start with the clock signal into the gate array. That's pin 8. Yeah, okay, 16 megahertz going into there. Okay, yeah, that one is totally fine. And let's look at the clock signal going out to the CPU. So yeah, we get some 4 megahertz there, perfect. And the one controlling the CRT controller, it's pin 40, okay, right next to it. Okay, and this one is 1 megahertz, so that's perfect. Notice also that it's not an even cycle, so it only activates every so often, and that's where the synchronization between the CPU and the CRT controller comes in. So far so good. The gate array is acting correctly as far as the clock signals go. So next, let's look at the sync signal generated by the gate array. So right there, and whoa, what is that? That is weird looking and it's not even stable. So the sync signal is active low. So it syncs when it goes to ground. I have no idea what those things are on top. This is not what a healthy sync signal is supposed to look like at all. What about the frequency? Is it more or less the same? This sync signal should happen with the horizontal sync, which is every 64 microseconds. That's not even right. That's 1, 2, 3, 4, a little bit more than a half times 20 microseconds. So that's not even happening every 64 microseconds. What is this? Am I in the right pin? I am on the right pin. Just in case, let's look at the horizontal and vertical sync coming out of the CRT controller. Horizontal sync should be this one. Okay, and that looks reasonable. And is this happening every 64 microseconds? Let's see. 12, no, that's pretty spaced out. I'm not sure the timing is right. The timing is right. And vertical sync should be much more spaced out. There you go. That should be every 20 milliseconds. 7 times 4 is 28 milliseconds. So even that frequency seems wrong. What is going on in here? Since I have a spare gate array of the same type, I'm just going to swap it out and see if anything changes. It could be that it's both the gate array and the CRT controller. It'd be weird, but it's possible. Yeah, we'll definitely get a lot of questions answered once we try the new gate array. Okay, and let's look again at pin 11. Okay, that same weird thing. That is really weird. And pin 14, same thing. And pin 15 for the vertical sync, same thing and same weird spacing frequency. Then it's likely that the gate array is fine, which is good. It's the most expensive chip on the whole board. And the fact that we're getting really weird frequencies from the CRT controller, but we're actually feeding it correctly a 1 megahertz signal, that tells me that there's something wrong going on in there. So I think I'm just going to pop it out and try a new one instead. Actually, before replacing the CRT controller, I realized there may be another reason why the frequencies are off. The CRT controller can be programmed to work in many different frequencies, and one of the first things the Amstrad does whenever it starts up is to initialize the CRT controller. But if for some reason the ROM was corrupted, it would fail to initialize it, and we would be stuck with some default incorrect frequencies. And that would make sense too, because horizontal sync and vertical sync look to be fine, they're just too slow. So to test that theory, let's try putting in the diagnostics ROM. That will override the computer ROM, and as you can imagine, one of the first things I do in there is initialize the CRT controller. And we still get absolutely nothing. Okay, so it's probably not just a bad ROM. There's got to be something else.
That, it turns out, is the right conclusion for the wrong reasons. So hang on to that thought for about 5 more minutes.
So the ROM was definitely worth a check. But that got me thinking. I'm still thinking that the CRT controller behaves correctly, it's just that wrong frequency. So if it wasn't a ROM problem, maybe there's something that prevented the CPU, the Z80, from initializing the CRT controller correctly. I didn't even bother checking the Z80 because we're getting some image on the screen. And if you have no Z80 at all, if your Z80 is not working, you'll get a black screen because the gate array is using some of the signals from the Z80 to generate the video signal. And that's why I've kind of dismissed it up until now. But I suppose it could be partially working, and the gate array is able to display some things, but some other functionality in the Z80 is not working and is not able to initialize the CRT controller correctly. So it's worth, at this point, examining some of the signals on the Z80 and make sure that everything looks okay. And as I was getting ready to check the Z80, look what I found in here. That is totally scorched. So I looked it up in the schematics, and this is actually, it's very interesting. This is related to the video out signal. It looks like this transistor is used to generate the luminance signal. So the signals out of the video connector are R, G, and B. There's a sync signal, which is what we've been seeing on the gate array. And there's a luminance signal, which I believe combines the intensity of R, G, and B together, plus the sync signal, all of them together, into a luminance signal. And this transistor and those resistors are used to do that. So the transistors pretty much add the voltages together, and I believe the transistor just boosts that signal. So that looks really bad and really suspicious. This is definitely on the end of the video connector. So I cannot imagine this would be possibly related to the incorrect frequencies that we're seeing. So it looks like there are multiple things wrong with this board. I could get into this right now, but I'm actually more interested in getting reasonable signals into and out of the gate array first. So as usual with the Z80, let's start just to see if it's alive. So that's M1. It's usually not that way. This tells me that the Z80 is working, but it's kind of stuck in a loop just doing knobs or doing a bunch of instructions that are all the same length, which is not normal. In refresh, this is for DRAM refresh, that's fine. Let's check that the reset line is correct. Yes, reset is high, that's fine. Read request, again, they're working, they're very periodic, so we can check some of the other control signals. So this is the interrupt signal, and that's low, and this is an active low, so that seems bad too. That is coming straight from the gate array, but it doesn't mean that the gate array is bad. We know that it's probably working correctly. It could just be that we sent an interrupt to the CPU and it never got out of it. Okay, so all of that is, confirming that I think the CRT controller is fine. I think it's just we're not initializing it correctly. So thinking some more along those lines, another possibility, if the ROM is fine and the Z8 is fine, is that it could be that the data bus was or is being clobbered by something. We could look directly at the RAM chips. Okay, that seems reasonable. Some activity there. It never looks particularly pretty. Oh. That one is totally left floating. That one, there's activity. Same thing. Same thing. They all look, they have something going on except for this one. And unless I did something wrong, yeah, that one looks like it's just floating there at 1 volt, 2 volts. So that looks really bad. However, that's probably not going to fix all our problems because this is just the RAM. And when I try to run the diagnostics programs from the ROM cartridge, it actually doesn't care about the output bit because that one is not connected to the data bus. So in theory, it should have been able to read the cartridge ROM correctly. So, But you know what? It looks really bad. Let's go ahead and replace it and see if that bit looks better after that, and it may help us along the way figure out what else is wrong. Okay, so let's see if the new RAM chip makes a difference. So in the output, yeah, we have normal activity. I think this was correct. This other chip was definitely faulty. It was outputting nothing. It looked like it was just, there was no output whatsoever. And this one seems to be working. So that's a step in the right direction. I don't imagine this is fixing the VSync problem. Oh, look at that, 50 Hertz. That's exactly right. And this is horizontal sync, but I know it's every 60, yeah, look at that. 8 microseconds times 1, 2, 3, 4, 5, 6, 7, 8. Wow, so that RAM chip fixed that. But when we tried running the diagnostics from ROM, it didn't work. That is really bizarre. I'm gonna have to think about that one for a while. So the question now is, are we getting some video out? Because this is not even connected. Or is this charred area over there preventing us from getting video? So let's connect it and find out. Oh, wow. I'm kind of blown away that this is working with this charred area over there. Okay, so with the diagnostics ROM in, oh, it's not even running it. So maybe that's why earlier this didn't run. Maybe there's something wrong with the edge connector or it's not clean correctly. Let's clean the edge connector a little bit better. It looks pretty clean, but I'm just giving it a quick wipe down with alcohol. Ah, now it works. Okay, the rest of the memory passes and it doesn't detect anything major, so that's very good. And just to be sure, let's put the bad RAM IC back in and try it with the ROM diagnostics program. And yeah, it does detect it correctly. So really, this was just because of the dirty edge connector. That was bad luck. So that was really unusual. Normally, bad RAM results in that gray square in the middle of the screen, but I suppose it depends on the bit and how it interferes with the rest of the computer. On the Amstrad CPC, bad RAM doesn't interfere with reading from the ROM because it's isolated by a buffer chip. But as soon as the initialization code in the ROM tries to use the RAM for anything, and I mean anything, like storing a return address for a function call on the stack, boom, it all goes wrong. I never thought too much about why we get that gray screen with bad RAM, so I decided to do what we usually do here at the Retro Lab and dig deeper to try to understand exactly what's happening.
Whenever the Amstrad CPC is reset, it starts executing code from the system ROM at address 0. And remember, as long as it's reading from ROM, everything's going to be fine. It's when it tries to read from RAM that things are going to go really wrong. And right away we get to the CRT controller initialization code, so that gets correctly executed. Shortly after that, it sets up the stack at RAM address C000, and that's the beginning of the screen address, but remember the stack is going to grow down, and it makes the first function call. That means that address 05F4 is added to the stack, and when it tries to return, the value we'll get, instead of 05F4, it's going to have 2 bits set to 0, and it's really going to be 05D4. In that particular case, it's going to be right in the middle of the CRT initialization data table, and if we interpret those as opcodes, we get this. In other words, total nonsense, which is likely to even do a return, which means we're loading another address from the empty stack pointer. So we'll read the first 2 bytes of the screen area actually, with the incorrect bit and all, and jump there. But that's even assuming we get this far, because the function we called at 1FE9 made some function calls of its own, which will never return to the correct place. So yeah, a missing bit in RAM creates a total mess and makes the CPU run crazy all over memory. Going back to our original question, how exactly is that setting the wrong frequencies in the CRT controller? I puzzled over this for a while, and the only good answer I came up with is if during the Z80's wild execution of code, it actually landed at address 05B4 without executing the code preceding it. That would load up the CRT controller with whatever data HL is currently pointing to. So I'm going to say that's the most likely place we're jumping to from somewhere and setting completely garbage CRT settings. I really wanted to see what effects other missing ICs had on the display. I didn't have any other boards with socketed RAM chips, but in the interest of science, I desoldered all the RAM ICs on this board I had in my repair pile and socketed them all. If it makes you feel any better, 4 of those RAM ICs were faulty, so I kinda needed to do this anyway. So let's see, starting from the top, what kind of effects each missing chip has. That one is the third chip from the bottom, which is the one that was failing on the other computer. And as you can see, it has the exact same effect, so at least that confirms everything is the same. So it's really interesting that we didn't get that gray square I talked about. Maybe that's something that only happened in the CPC 6128? Now I'm not really sure, to be honest. Every version of the ROM is going to do something slightly different, depending on the exact contents of the ROM, and even depending on how the RAM chips fail, high, low, or maybe even semi-random. So in any case, I guess that gray square pattern is not nearly as common as I thought it was. And just for completeness, and since it was something I mentioned earlier, if I remove the Z80, we get no video signal at all, just like we expected.
So what about that charred area? It doesn't seem to be affecting anything, but we should at least make sure that everything is the way it's supposed to be over there. So just give it a really quick brushing with alcohol and the black stuff disappeared completely. So I wonder if that wasn't burned, but it was actually like a marker or something, and I thought it was burnt. I mean, it had all the telltale signs, but it seemed to just disappear right away with alcohol. And the other thing I just wanted to test that there was nothing broken. So the resistors are in place, they're not cracked. And yeah, they seem to be fine. So I want to check the luminance signal, but before looking at it, I want to look at the signals that it's composed from. That way I know what to expect. So this one over here is red. And okay, those spikes make sense. That's actually the text that we have on the screen now that it's working. This is G, I imagine. Yep, similar thing. And blue, we'll probably see more of it. Exactly. So because most of the screen is blue, and those low areas, those are the borders, I think. And then we have the sync signal, which is the one that before had those weird spikes. So now we have a little bit of noise, but those weird extra spikes are gone. So I wonder if that was related to that particular RAM IC. Huh. Okay, but we'll go back to that in a second. Now that we know what those things are like, the luminance signal is supposed to be all three of them put together. And I believe the output is this part of the transistor. And yeah, actually that's exactly right. That's probably blue combined with RGB in those places and the sync signal. So yeah, that's exactly right. So yeah, the transistor seems to be working. I don't think there's anything we need to do over here. That maybe was a false alarm, a very convincing false alarm. I am very curious about the sync signal though. Yeah, I mean, now it looks perfectly fine. So I'm going to remove this chip, and what do we get now? Oh, it's not exactly the same as before, but it's definitely very related. So why would this missing RAM chip affect the sync signal? That's quite a mystery. And to make it even more of a mystery, or maybe to give us a clue, I don't know, if I plug in the video cable, even with the missing chip, the sync signal looks fine.
After thinking about this for a bit, I realized that the weird spikes we're seeing on the sync signal are the same that we're seeing on the Luminance signal. In other words, it's the R, G, and B signals that are bleeding over to the sync. That explains why with the RAM chip on, we see some of that quote-unquote noise. That's not noise, those are the pixels of the text on screen. And when I remove the chip, we see 3 or 4 big blocks, which is probably whatever is displayed on the screen with the crazy Z80 execution due to the missing bit. So, how come this only happens when the video cable is not connected? If you look closely at the video signal circuit, you'll see that RG and B have pull-up resistors, but the video cable isn't connected and the signal level is pretty high, probably around 4 volts, whereas the sync one was pretty low all along. So that makes it that some of the current travels down to the sync signal since they're all connected through a resistor network. When the video cable is plugged in, it has a certain resistance at each color channel, and that drops the level of the signal and it doesn't interfere with sync anymore. So what I first thought was the main problem with the machine, it turns out was something totally normal, and the only real issue here was the faulty RAM chip and the fact that it was setting up random frequencies in the CRT controller. I gave the Amstrad a quick cleaning, and just to make sure that everything is working correctly, let's run the latest version of the diagnostics program. Lower RAM is fine, ROM is fine, and the keyboard and joystick all check out as well. Excellent, I think this machine is ready to go back to Marcos. So there you have it. I was so sure it was a problem with the CRT controller, and it turns out it was caused by a single RAM IC. That just goes to show that you can always start with theories based on what you see, but you should follow up on them and check them because they'll often surprise you. Anyway, I hope you enjoyed that episode. If so, please give it a thumbs up and subscribe to the channel. Oh, and I keep forgetting to mention this, but if some of you prefer to get notifications of new videos through email, I've set up a mailing list just for that. You can find a link to that in the description. In any case, see you next time. If you enjoyed this video, please consider supporting Noel's Retro Lab on Patreon or joining the membership on YouTube. Not only is that the best way to support this channel and allow me to continue making more videos, but you also get some extra perks like early access, ad-free videos, and more. Thank you again to all the supporters. See you next time.